Now here's where I come clean. Here's where I show you where these formulas come from. And I'm going to show you in a way that's not going to hurt. Okay? I told you that when I did this up front, people fell asleep. But now, it's quick and painless, and now it's going to mean something to you. Watch. If I take a box, and I move it up a distance h, and I do it in a special way, the box was already moving slowly when you opened your eyes. And it kept moving slowly at a constant rate all the way up. Now if I look at the buckets, down here, because it's moving, it's got some kinetic energy. But if I call this height 0, I don't have any gravitational energy and there's no springs in this problem. So that's my total energy. When I get up there, I've got exactly the same amount of kinetic energy that I started with. I did not fill that bucket. But the gravitational bucket got filled. And that changed the total energy. Now the only way you can change the total energy is to do vary. And if the total energy got bigger, that means the vary was positive. Well, what did the positive vary? The hand. And I can calculate that very easily. It's the force exerted by the hand times the distance. Well, the distance is just h. What about the force by the hand? Does this hand have to push more than the weight, less than the weight, or equal to the weight to make it go up? Equal. It's going up at a constant velocity, zero acceleration. So the force by the hand is equal to the weight, which is mg. And that's the distance, is h. What was done to fill up that bucket was mgh. And that's my formula for gravitational potential energy. You see what we did? We contrived a way to fill only that one bucket by doing work. And because we have a formula for how we do work, we were able to get a formula for how we fill the bucket. Let's try it again, but this time let's try it for the spring. Okay? I have a spring that came out of the box that long. This is the equilibrium position for the spring. And then I take that block and I start from rest. This is important. I start from rest. I push slowly and I stop. I start from rest and I end at rest. Now, again, the goal is to only fill one bucket. Since I start from rest and I end from rest, there's no kinetic energy. Since I stay on the floor, there's no gravitational energy. The only bucket that gets filled is the spring bucket. I go from no energy to some energy. And that means my total energy bucket goes from nothing to something. By the Varick energy formula, that can only happen if positive Varick is being done. Well, I can calculate that Varick. It's the force times the distance. Well, the distance is just delta S. And the force is given by Hooke's law. Hooke, 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 Hooke. And that says that the force by the spring is equal to K times delta S. Now if I want to push that block at a slow constant rate, I have to push just as hard as the spring, which is K delta S. So if I take my push of K delta S, I multiply by the distance of delta S, I get K delta S squared, which is, that's the energy stored in the spring. Again, we did it. Pretty nice, huh? We good?
Yes.
There we? Oh, come on. People, you're better than that. You're better than that. What?
What about the 1/2?
What about that 1/2? Are we gonna make me a liar over a half? Yes. Let's think about that push. As I start pushing this spring, initially, it's not very hard. The spring's not very compressed. I can push it easy. And then it gets more compressed, it gets harder. And then it gets really hard. And then it gets really hard. So it goes from easy to hard. The only place where I'm pushing with that value of K delta S is there, when the spring is already compressed by delta S. I start out pushing with nothing. Which force you want to use when the force is changing? The biggest or the smallest? Average. The average. And the average between that biggest and smallest is halfway in between. And so what I want to use is the average force times the distance. And that gives me the half. And that gives me the formula for filling up that spring bucket. Now folks, there's another class that meets in this room. They call themselves calc-based physics. It's filled with a bunch of engineers. And they derived that formula using calculus. And they felt all warm and fuzzy about themselves for doing so. I'm thinking they wasted their time. You have to use calculus to derive that formula. You're not thinking very clearly. Okay? This, all we need is the average force. The average force. Are there questions on those derivations? Was it indeed painless? Nod your head. Good. Thank you.